on the videos, whenever you step away from that, you can't hear it.
I know you can't. I try to, I know. You got to crank it up, I guess. But no, I understand. With this little mic, you can't pick up well beyond it. So, remember work is F times D times cosine theta. So on the first OpenStax question, you have some questions where you're just finding the work for a force. I think it's something like you have an object where you're pulling it along with a certain force. They don't tell you what the force is, but they tell you that after a certain distance that it has some velocity, say 10 meters per second. And they ask you a variety of questions about it. First of all, the question is, this distance is given. Let's say that this distance is, I don't know, 5 meters. And this angle was given, I don't know what it was, I'm just making up numbers, 30 degrees. There's something along these lines. And they ask you a number of questions. One of the questions is, what amount of work does the gravitational force do? Remember, for work, there needs to be a force and there needs to be a displacement. And in this case, there's a horizontal displacement, but the gravitational force, right, is vertical. So what is the work that the gravitational force does? It does no work, right, because the angle between FW and the displacement is 90 degrees, and the cosine of 90 is 0. So so there's no work done by the gravitational force. Okay? Y'all clear on that? And then it also asks how much energy is gained by the object. Pretty sure it gives a mass. Let's just say that the mass is 2 kilograms. Or how much work is done by this force. And if you wanted to know the work that's done by the force, here, what is the work done by this force? Well, by the work-energy theorem, we know that work is equal to a change in energy. So if we can figure out the change in energy, then we can know the work that's being done by that force. Right? So how would I determine the amount of work that's done by this force? What equation is that? But I don't know F. Like, F isn't given in the problem. I have no idea what F is. No, you're thinking gravitational potential energy, so you said... No. We had another type of energy. What was that? We had potential energy, and what else? You're right. So kinetic energy is 1/2 mv squared. So if I want to know the amount of work that's done by this force, all I have to find out is what is my change in energy. And I'm going from an energy, kinetic energy here, equal to 0, over to here, to a kinetic energy equal to 1/2 mv squared. So my kinetic energy then is equal to 1/2 of 2 kilograms times the velocity, or the speed, which is 10 meters per second. That's squared. So that's going to be equal to 100 joules. So I know then that my work that's done by that force is 100 joules. And I know that it's positive work because my energy is increased. So a couple of questions it asks. What work is done by this force? This unknown force, you don't even know what the force is. And then also, what is the work done by the gravitational force? We already said that was what the gravitational force was. It was 0, right? Because they're perpendicular to one another. And if they're perpendicular, that force does no work. If the force and the displacement are perpendicular. So another question that it asked, you had, what is the work done by the gravitational force? We said that was 0. What is the work done by F? And that's just, we just find that by asking what is the change in energy. And then another question to ask is, what is F equal to? Well, how in the heck am I supposed to find F? We could go through it the hard way. Like, you could figure out what is my acceleration to get up to 10 meters per second over a distance of 5 meters. Like with all our kinematic stuff, there is a way to work that problem. But the easiest way to do it is to say, well, look, I know that my work is 100 joules. That force does 100 joules of work. And so that's equal to F times D times cosine of theta. Right? You with me on this? It's your very first problem on the OpenStax, and it's a little more difficult than some of the others, so I wanted you to go into it with confidence so you don't freak out. In fact, go ahead and do it this evening, and then you'll find that the other problems are a little easier. Since you know D and you know cosine theta, you can solve for that F. Okay? I'm going to leave you at that. Well, let me show you another type of problem. We sort of worked a problem like this. Oh, no, we didn't work one today. But you'll find some like this on the old test, and maybe we'll look up one. But let me just show you the type of problem that it is. First of all, let's say that I have an object, and it's at a height equal to, I don't know, 5 meters. And I drop it. Its initial velocity is equal to 0 meters per second. And then I let it fall. It goes down, and it goes to the ground. And I want to know what is the velocity here just before it hits the ground. This is our conservation of energy. We talked about this in class today. My energy initial is equal to my energy final. I know that's true because I only have conservative forces acting here, right? Only gravitational forces. We're assuming no air resistance, no friction, no non-conservative forces that would lose energy. So if the initial energy is equal to the final energy, then I can say that all the energy that this object has up here is going to be equal to all the energy that it has down here. What type of energy does it have at the top? It has potential energy, mgh. And at the bottom, what type of energy does it have? Kinetic is right. So it only has 1/2 mv squared. So the initial energy is only potential. No kinetic energy, because it's not moving at the top. It's just like I'm just holding it up here, and then I let it go. And I want to know the speed just before it hits the ground. And then at the bottom, no potential energy, because h equals 0. Down here, we'll call this h equals 0. So my energy is 1/2 mv squared. Notice here that my masses cancel out. That's a good thing, right? Because we know from chapter 2 that it doesn't matter the mass of your object, that it's still going to fall at the same acceleration, that -10 meters per second squared. So it's a good thing here that my speed, my final speed, is not dependent upon the mass. That if I had a heavier object, it wouldn't fall at a faster rate, even though the gravitational force is bigger. Which there was a question on the test, right, where I think about where you had a 30 Newton and a 20 Newton object. You remember that? They fall at the same rate because they have the same acceleration due to gravity. Don't need to worry about the old test now. We're looking forward now. So here I would find the speed. If I want to find the speed, it's going to be the square root of 2gh, which is going to be the square root of 2 times 10 meters per second squared, that's g, times h, which is 5. The square root of 100, that's 10 meters per second. There was a very similar problem to that one, all right, on your OpenStax. You could work this in reverse, right? That if I have something that I give a certain initial speed at the bottom, how high does it go? And you'll see problems like that. We'll do one in class next week. If it goes up to a certain height, what was the speed down here? If I give it a certain speed, then how high will it go into the air? It's the same problem. Only kinetic energy here, only potential energy here. Because it stops up here, right, at the top of the trajectory. You can do that? Do it this evening. Like as soon as you leave here, while it's still fresh in your mind, go ahead and pull it up on your laptop and or on your computer or whatever, and do that problem on OpenStax, okay? Please, for me, you'll do it. 100% on OpenStax. I would love for everybody to get 100% on the OpenStax assignment, because it's a test grade, man. It's a test grade. Okay? All right. Let me show you another type of problem. Like you might think this is different, but it's not different. You're just sort of thrown off because it's an inclined plane. But the beautiful thing about energy and work is that it makes all these problems that we've been doing a lot easier. And we'll find that with momentum too, when we get to momentum in the next chapter, that we'll encounter situations that we could work sort of the old way, the hard way, with Newton's laws and kinematics and all that business, and it's kind of hard, and exam 2 was kind of hard. I mean, even y'all's exam 2, right, Miranda, was hard? I heard about it. This is a tough exam. Exam 2 is the hardest exam you'll have maybe all year, except for maybe exam 2 next semester. Y'all get to look forward to that one too, right? Because you get voltage and current, and they're sort of strange ideas. Anyway, looking forward now, right? We're looking forward? All right, so we have, let's say that we have an object here, and it's at a height equal to, say, 2 meters, and I want to know how fast is this object going after it travels a distance here of, say, 4 meters. How fast is it going down here at the bottom? What is V at the bottom? It's the exact same problem. I say I have potential energy here, I have kinetic energy here. I said I'm equal to one another. I'm assuming no friction, though we'll throw in some friction in just a minute. It changes the problem a little bit. But if I assume no friction, then I say, all right, well, the potential energy at the top plus the kinetic energy at the top. I'm just writing out the whole conservation of energy equation that we wrote this morning, is equal to the potential energy at the bottom plus the kinetic energy at the bottom. And then I go through and I say, oh, this is 0 and this is 0. With me, folks? With me? Potential energy at the top is mgh. Kinetic energy at the bottom is 1/2 mv squared. Notice my masses cancel here. I might give you the masses on these problems, but I might not too. Usually you don't need it. I know you sort of freaked out on that problem where I didn't give you the maths. Y'all shouldn't have. I did it in the help session. You remember doing that problem in the help session? I did that problem. The help session the day before the exam. Man, that's a sweet help session because I got the exam on my mind because I've just been working on it. And I don't mean to tell you questions that are on the exam, but I often do. So y'all come to that help session particularly. Do you remember me telling you all those test questions that you had? I did. I really did. Several of the questions. All right, so what was I saying? Here, if I want to know V, it's square root of 2gh, which is going to be the square root of 2 times 10 meters per second squared, that's g, times the height, which happens to also be 2 here. So it's the square root of 40, oops, which you know is about 6 point something. All right, let's say, what is square root of 40 exactly? So it'll be important. What is it? 6.3? 6.3 meters per second. So let's say, and there's a problem like this on the OpenStax, that if at the bottom your velocity is not 6.3, but instead I tell you that you have this situation and the velocity is equal to 5 meters per second. Well, what the heck is going on? Because I know that this object should be going at 6.3 meters per second, but then I clock it and I find out that it's actually going at 5 meters per second. So what has happened? Right, I've had a non-conservative force. I've had a force that's lost a little bit of energy, and now this object is going slower than it should be going. So my problem looks a little bit different. It's going to look like this. It's going to be the potential energy at the top is equal to the kinetic energy at the bottom plus the work that's done by friction. Or if you really want to be rigorous about it, I guess you'd really write it like this. Potential energy at the top minus the work done by friction because it's a negative value, right? That work, it takes away energy, is equal to the kinetic energy at the bottom. But these are the same expressions. You understand what I'm doing there? I'm treating this value as a positive value, but I'm putting my negative right there, because work done by friction is usually negative, right? Because if the force and the displacement are opposite one another, negative work, meaning I take away energy from that object. Okay, so I want to know what is this frictional force. And you have a very similar problem on the OpenStacks. I think actually there's a problem that asks for the coefficient of kinetic friction. And we can talk about that. But first, let's find the frictional force. So I'd say the potential energy at the top, that's m times g times h, is equal to 1/2 m times v squared plus the work done by friction. What's the work done by friction? How do we find work? Right, F times D times the cosine theta. But in this case, the cosine theta bit just goes to 1 because that angle is 0 degrees. Actually, the angle is 180 degrees. So because the displacement and the force are in opposite directions, right? This is 180 degrees. With me? All right, so it's just going to be F times D, where my distance D is this value, that 4 meters. Alrighty? So I can figure out what F is. In this case, my mass doesn't cancel out if I'm just looking for the frictional force. But really, the frictional force does have a mass hidden inside here, right? How is the mass hidden inside this variable? It's the what now?
Like the mass times acceleration.
Sort of. Not exactly. How is the frictional force dependent upon the mass of this block on this inclined plane? What's that? Similar to that, but our frictional force is equal to mu times what? The normal force. And the normal force is proportional, is related to the mass, the weight, yeah. In this case, it's not equal to the weight. So on your OpenStacks, you have a problem where it's on a flat surface, and in that case, the normal force is equal to the weight. Okay? You with me? All right. You want to go ahead and work too, Miranda? Okay. You're welcome here anytime you want. Okay, so I want to find F. This is not too difficult because I know everything here. F is equal to mgh minus 1/2 mv squared divided by d. Just a minute to look and see. I subtracted 1/2 mv squared from both sides and got the numerator, and then I divided F times d by d in order to isolate F and get it all on its own. So, see, I didn't give the mass up here, but let's just give it. Let's say that this is 3 kilograms. So I have 3 times 10 times 4 minus 1/2 times 3 times 5 squared divided by d, which was 4 meters. Oh, I'm sorry, I made a mistake here. M times g, that's right, 2. Thank you, Drew. Times 2. Notice the two different distances and the role that they play. The mgh, it doesn't care about the distance here. It only cares about this. Remember, because conservative forces are path independent. It doesn't matter if you follow this path or if you follow this path. You still have the same change in energy for conservative forces because they don't lose any energy and they're path independent. Doesn't matter the path that you take. So let's see, that's 60 minus 2.5 times 25, 38. divided by 4. Am I getting this right? 22 divided by 4, 11 divided by 2. 7 newtons? Is that right? Okay, so that means that the frictional force has done work, and that work is equal to 7 newtons times the distance, which is 4 meters. It has done 28 joules of work. It's actually done negative 28. It's taken 28 joules away from that object, and that's why that object is going slower now. Alrighty? Let me think. There are some problems too, like the roller coaster problem. I'm pretty sure if they aren't on the OpenStax, you'll definitely see them on the exam. Miranda, I'm pretty sure you'll see these too on your exam. You want to do one of those? Yeah, let's do one. It was a very similar question to this, except it was on a horizontal surface, and it makes it a little bit easier. You have a force. Let's say that the force was 5 newtons, and it acts over a distance of, say, 4 meters. And at the end, let's see, I have to think about it. I have to make up a number that works. 20 joules. Oh, shoot. Give me just a minute, okay? Does it give the answer? It doesn't. Good, okay. Let's see, we're looking at, gosh, I can't read this, but I'll use it for me. It says a cardboard box of unknown mass is sliding upon a horizontal frictionless surface. The box has a velocity of 4.56 meters per second when it encounters friction. Oh no, friction. And then it slows down. It says slide set 0.7 meters, and then it has a velocity of 3.33 meters per second. What is the coefficient of friction? How would we do that? Any idea? Similar, right, very similar. So I know that before it has the friction, let's draw a picture. I'll just give you some different numbers. Well, let's see. This is what I know. I know that here it has a speed of, say, 4 meters per second, and here it has a speed of 2 meters per second. And we'll make this 4 meters. And I want to know what is mu k. I know here it has a certain amount of energy. And I know here it has a certain amount of energy. Did it give the mass? It did not, right? Yep, that's all that we know. All right, so let's just sort of go from there. Listen, sometimes you encounter these problems and you're not really sure how to work them. But as you start sort of thinking about the things and start writing out equations, eventually it'll be clear. Because right now the big problem that we have is what's the mass? And y'all are getting to a point now where you should, I know that you'll really love to put in numbers, right? You love to put in numbers. You don't like to put in the variables. But like, for example, that question where you didn't have the mass, if you would have put in the variables for FW, then you would have seen that those two m's would have canceled out. Like that would have really helped you on that problem on the test. The thing sliding down the inclined plane where I just asked you the acceleration but didn't give you the mass. So it's a good practice to write out the equations with all the variables and then manipulate the equations and then put in the numbers. But I know that y'all don't like doing that. Nobody likes doing that. But it's a good practice for you as you move here and into your more upper level classes. So I know that the work done by friction is equal to Fk times the distance. And that's equal to the change in kinetic energy, to the kinetic energy that it had initially, or actually, final minus the kinetic energy initial, but remembering that this is a negative value. You follow what I'm saying there? The final kinetic energy is smaller than the initial, so this is going to work out to be a negative value, and we need to remember that the work done by the frictional force is also negative. If you didn't remember that, it would have sort of popped its head up, because you would have been, oh, there's a negative here, and it's saying that I have a negative equal to a positive. It would have sort of freaked you out. And then further, we can say that this is equal to mu k times the normal force. But remember, the normal force is m times g. Right? This is my normal force because it's on a horizontal surface, and then times my distance. And then that's going to equal to my 1/2 mvf squared minus 1/2 mvi squared. Now look, that mass, which I wasn't given, I'm sort of freaking out about, it cancels out. And I know everything else there but this value. But I can solve for that. Let's go ahead and do it. I have negative mu, or let's just solve it for mu k. Mu k is equal to 1/2 vf squared minus 1/2 vi squared divided by negative g times d. And now that I got everything all set up, nothing really cancels out anymore, but I can go through and put in the numbers. So I have 1/2 of vf. Vf is 2. Minus 1/2 of vi squared. That's 4. I'm getting these values from up here, here, and here. Divided by negative 10 meters per second squared. That's my g value, times distance, which is right here. That's 4 meters. And then that will give me my value for mu. That's 4 minus 8, negative 4, divided by negative 40, which is 0.1. That's my coefficient of kinetic friction. If you had gotten your sign sort of messed up along the way, you would have found that this was a negative value, probably. But you say, well, coefficient of kinetic friction, that can't be negative. That has to be a positive value. It doesn't really mean anything to be negative. Okay? That's in the second OpenStax. So while it's fresh on your mind, I would go ahead and do that. That's one of the more difficult problems. That's what I want to show it to you. Or John, you asked about it, right? Did you ask this problem? Yeah. It's a good problem. Might see it on the exam coming up. And not that long, the exam. Not long from now at all. Yeah. Yeah, VI is 4. Right here? Yeah, that's VI, and it's 4 squared.
Okay.
This is my final kinetic energy minus my initial kinetic energy. Really, I just want the difference in those two kinetic energies, and then I'm going to divide that by my g times d. Okay? What else you want to do? I told my wife that we wouldn't last the whole hour, so if that's okay, we'll stop at about 3:45. But while we're here, let's do something else, huh? Yeah. Which one? This one right here?
Yeah.
Negative 4 on the top. Well, let's see. Did I do that wrong? Half of 4 squared is 2 minus, oh yeah, that's not right, is it? Minus 8. Yeah, so that should be minus 6 over 40. Gosh, I just missed that problem. And what is it? What if you divide 6 by 40? What's that? 0.15. Okay? Thank you. Y'all can dock my pay. What if they dock my pay every time I got a question wrong? Yeah, it'll be a pauper. I used to wait tables. And our manager, our GM, he always threatened to dock our pay every time we did what?
Drop.
Every time we broke a dish. It's like those plates cost like $40 each because restaurant dishes they're kind of pricey. Huh? Yeah. All right. Let's see. What do we want to do? Huh? Yeah. Let's take a look. Yeah. Oh, let's see. This is from. Let's not do this one because this one's in your book, right? F16. You have 15. Okay. Yeah, let's find. There's one here somewhere, I think. Well, let's not do this one. Let's do the other one. Often I'll put them in like a sequence. So we have 15 in the book. Well, let's do this one. We might do it again in class. Is that okay? All right, look at number 2. So I have this problem. I have lots of different points on this. I want to go through initially and just ask myself, what is the what is the types of energy this object has at different points? And so, for example, up here at point A, the object has kinetic energy. It's not going to let me do that. Hold on. At point A, this is A, B, C, D, and then up here is at E. At point A, it has both kinetic energy and potential energy. I know that it has kinetic energy because the velocity at the top, or the speed at the top, is 4 meters per second. So it's moving there, has kinetic energy, and it's at a certain height, so it also has potential energy. Down here at B, what type of energy does it have? Only kinetic, right. Because H equals 0, there's no potential. Here, it has kinetic and potential. Similarly, at D, it has both kinetic and potential. What about at E? And then the problem, well, it comes to a rest. It doesn't say that right there, but it comes to a rest at point E. What type of energy does it have? Only potential, because V equals 0. Now, in number 2, it asks, what is the speed of the cart at point B, right here? And so what I do is I take this energy, which I know because I know its height, and I know its speed. We don't know its mass, but we're going to write out the equation. We'll see that the mass goes away, right? Because we're talking about conservative forces here. The mass doesn't matter. So I say KE plus PE equals just KE. This will be for A, and this is at B. So I got 1/2 mv squared plus mgh equals 1/2 mv squared. Like I promised, your masses cancel out. You'll find that that's always true. Next week on Monday or Wednesday, we'll get to springs. And springs, the energy is not dependent upon a mass. And so that mass is not going to cancel out. But we'll deal with that when we come to it. But here the mass does cancel out. And what am I looking for? I'm looking for this value. So I'm going to solve for that. Let's see, we can just go ahead and put in some numbers here. I have 1/2 of the speed, which is 4 squared, plus 10 times 10. That second 10 is the height at point A, equals to 1/2 v squared. So 16, 8, 108, 216. Root of that is 15 meters per second. So solving that for V, I get V equals 15 meters per second, 14.7. Okay? But if we wanted to know, the next question asks, what is the height here? What is this H equal to? It's the same question, largely, except instead of saying, the kinetic energy at A plus the potential energy at A is equal to kinetic energy at B, we're just going to change this just a little bit and say that this is equal to the potential energy at E. Because you see, the amount of energy that it has at A is the same as it has at B, C, D, or E. They always have the same amount of energy. That's what the conservation of energy says, that total amount of energy does not change. Okay? So if I wanted to find the height, I would say the kinetic energy, well, let's see, it would be 1/2 mv squared. This is at A, plus mgh at A is equal to mgh at E, at point E. I'm leaving off that 1/2 mv squared because VE is equal to 0. So it just goes away, that whole term. You'll find that's true, that often there are terms that just disappear because you don't have kinetic energy or you don't have potential energy at that point. Either it's not moving, so no kinetic energy, or it's at ground level, which we'll call H equals 0. Just a little aside, this doesn't really come up too much in our class because we always take ground to be H equals 0. But I can call right here 0. Right? I can set my coordinate system wherever I want. And so if I call this 0, that means that if I go up above it, I have positive potential energy. But what if I call this 0 and I go down below it? What does that tell me about the energy? I have negative. Yeah, I do have negative. And it's not too important now, but next semester when we get into electricity, we'll find that we can have negative potential energy in it, and it means something. Here, I mean, it means something here, but it's not very useful for us. So we'll always take the ground level as our reference point. So anyway, here if we wanted to solve this for HE, again our masses cancel. That's good because we don't know it. This goes away, that whole term. And it's just going to be half of VA squared, which is half of 4 squared, plus 10 times 10 divided by this G right here, divided by 10. That's 11 meters. 11 meters. Isn't that right? 8 plus 100 divided by 10. Yeah, 11 meters. So it would be E right there. Okay? Back to the work. How y'all feel about, yeah, Courtney?
For number 4, like the next question, would it be B?
Let's take a look. So what describes the cart's energy at D? What do you think it is? D?
That's B. I put B.
You put B? At point D.
Oh, no. It's D.
Is it D or B?
It's D.
You sure?
Yeah.
What do y'all think? Is it B or D? At this point, right here, what type of energy does it have? Does it have potential energy?
Yes.
Yes, because it's at some non-zero H. Does it have kinetic energy?
Yes.
Are you sure?
No. No, it hasn't.
It does have kinetic energy because it stops up here, right? So at this point, it's still going. It has some speed, and then it goes up higher, and it stops. In fact, it's always going to have, well, never mind. Just forget I said that. I know that it stops up here. So it's going to still be moving right here. It has both potential and kinetic. So D is right. You'll need somebody with you at exam time to say, are you sure? Are you sure? That wouldn't work, would
Just do
it?
that in the middle of testing.
Yeah.
So you guys can help me.
I know.
If
Yeah.
we have time, it's the next.
Yeah. I've been trying, my wife said that somebody told her that you can't breathe in my exam or you'll lose time and you run out.
Right.
That's not really true. Like, I can work through the exam in 25 minutes. That's with explanations and all. But like, I know it really well because I wrote the exam. But if you know it really, really well, then you can work through it in the allotted time. But I understand. The next exam will still be the same length, but just because the material is, it's easier, I think. This is easier, right? Is this easier for y'all? Easier? Y'all try that OpenStax. I think that you'll try it today, okay? Like, look, we're going to stop now, so you have another 15 minutes. You can get like 3 questions done in 15 minutes. Or maybe 1 question done in 15 minutes. All right? All right. Any questions, or are we going to wrap up?